This is Physics 2212 Lab 3 circuits. The purpose of this lab was to observe and understand the current and voltage in circuits with resistors and capacitors and measure the electric current in a circuit and the potential difference across the circuit. We calculated the resistance of the 47 ohm resistor to be around 57 ohms and the 100 ohm resistor to be around 114 ohms with error. The time of charging and discharging a resistor was about the same, and the time of charging and discharging doubles as we double the resistance. Some fundamental physics concepts and principles. We have Ohm's law rearranged to be R equals delta V over I. Resistance is equal to the potential difference over the current. Another concept that was important was charging and discharging a capacitor and the behavior of resistors in circuits, along with components in parallel versus components in series and how that affects the current flowing through a circuit. Part one of the experiment, we had the system was a circuit, the surroundings were everything else. The components were two 1.5 volt batteries, two resistors, one was 47 ohms and one was 100 ohms connected in series, and two ammeters. And on the right is the circuit diagram and a picture of our circuit. The data we got was at the initial readings on both of the ammeters were about 0.015 amps. After converting the second ammeter to a voltmeter, the first ammeter read 0.0002 amps and the voltmeter was negative 0.27 volts. The potential differences across the 100 ohm resistor was negative 1.8 volts, across the 47 ohm resistor was 0.9, and across the batteries was 1.4. The total was 0.4. It technically should be 0 across the entire circuit, adding all those up, but there was probably some human error or a faulty multimeter involved in the readings that we saw. So calculating the resistance from these, the 47 ohm resistor, you just take the potential difference and divide by the initial current reading. So we got 57 ohms for the 47 ohm resistor and 114 ohms for the 100 ohm resistor. Again, error probably contributed to the fact that these are not super close to what they're actually supposed to be. When we connect the voltmeter across the 100 ohm resistor, nothing happened to the ammeter reading, and then when we replace the voltmeter with an ammeter in parallel with the 100 ohm resistor, the current increased to 0.044 amps. Part two of the experiment, we used an RC circuit. The system was a circuit and the surroundings was everything else. The components were two 1.5 volt batteries, a 10 ohm light bulb, a 20 ohm light bulb, which we switched out, and a 0.2 F capacitor. The experiment, we measured the time it takes to charge and discharge the capacitor with each light bulb as our marker for if it was charged or not. And then possible error was human error in using the stopwatch, not exactly clicking start when it started. Our data, the 10 ohm charge time was 12 seconds and discharge time was 3 seconds. The 20 ohm charge time was 33 seconds and the discharge time was 39 seconds. So the time doubles as the resistance doubles. The charge and discharge times are about the same. There was probably some human error with the stopwatch on the 10 ohm discharge time. And the bulbs stay bright and slowly get dimmer. Start bright and slowly get dimmer, sorry. So the what if question, what if you charged a capacitor with no resistor in the circuit? How quickly would our ideal model predict the capacitor reach full charge? And would this prediction happen in real life? Use an ammeter to measure how long it takes to charge the capacitor when connected directly to the battery and the ammeter, and discuss why the measured time is different from the predicted time. So in an ideal model, the capacitor would charge instantly. However, real wires have little resistance, just slight, which would make it take a bit longer, but it would still be pretty fast. So the measured time would not be the same as the predicted time because these wires would provide a little bit of resistance and make it go just a bit slower. Thank you.